Welcome to episode 2, part 2 of everything you need to know about JPEG. Last episode, we were introduced to markers and began the decoder that takes JPEG files and reads the data for each marker. We left off with the start of frame marker for baseline JPEGs, which defines, most importantly, the height and width of the JPEG, as well as the number of color channels. And before we move on, there's one more detail to clear up about the start of frame marker. We mentioned that for a YCBCR JPEG, the 3 color component IDs will be 1, 2, and 3, even though you might expect the IDs to be 0, 1, and 2. We've already accounted for this in our code so far, but as it turns out, you may run into JPEG files every now and then that aren't exactly consistent. Now, I have a JPEG file to show you that is inconsistent with respect to the start of frame, but unfortunately, that file has a marker that we have not talked about that appears before the start of frame marker. So we have to handle that new marker first before we are able to detect the problem with the start of frame. So hold that thought. We will get right back to this last issue with the start of frame after talking about the next marker. So that marker is the define restart interval marker. This is an aspect that I have not mentioned up to now, but it's pretty simple. In episode 1, I said that an MCU is compressed completely independently from all other MCUs so that you can focus on a single MCU at a time. And that's mostly true. For every position in each MCU from 1 to 63, they are compressed completely independently. The only exception is the coefficient at position 0. For every MCU, the coefficient at position 0 is called the DC coefficient, and from positions 1 through 63 are called the AC coefficients. For every MCU, the DC coefficient is stored as a relative value relative to the DC coefficient of the previous MCU. For the very first MCU in the image, the DC coefficient is not relative to anything, so the coefficient you extract from the file will be the coefficient that you use. And let's say that coefficient value is 20 as the DC coefficient for the very first MCU. Then you move on to the second MCU, and the value you extract from the Huffman coded data is 10. What that actually means is the DC coefficient for this MCU is 10 greater than the DC coefficient of the previous MCU. So if the next DC coefficient you read is 10, you add a 20 because that is the previous DC coefficient. And then the true DC coefficient this time is 30. Then the next MCU, its DC coefficient will be relative to 30. You could also read a negative DC coefficient. Let's say for the next MCU, you read a DC coefficient of negative 15. Again, you add the previous DC coefficient to calculate your true DC coefficient. And then this will be the relative value you use when decoding the next MCU. And this process of adding the previous DC coefficient would be continued for the entire file for every MCU. But a restart interval changes that. A restart interval is optional, and if it's not present, then you continue this adding of the previous DC coefficient for every MCU. But if the restart interval is present, it tells you how often to reset the value that you add back to 0 in terms of MCUs. So if the define restart interval marker tells you that the restart interval is 4, then after 4 MCUs, you add 0 to the next MCU. So if this was the 4th MCU, and on the 5th MCU, you read a DC coefficient of 25, you add nothing to it. And the final DC coefficient is 25. But then this, again, still becomes the value you use to add to the next DC coefficient. So the next time, you add 25. The restart interval simply resets this value to 0 every 4 MCUs. So the define restart interval marker has the value dB, then the length, which is 2 bytes, and it must be the value 4, and then the restart interval, which is 2 bytes, and is a 16-bit unsigned integer. And that's all there is to it. It's a pretty simple marker, so let's add it to our decoder. For starters, let's add the restart interval to our header struct. And default to 0. 0 is going to mean the same thing as never. And if we ever come across a restart interval marker, we will set this to a non-zero value. Here again is our marker reading loop. Here we will check if current equals define restart interval. Let's add this right here. And then we need to add this function next to our other functions for reading markers. So we'll put that right here. Print our message like usual, and read the length like usual. And for this marker, all we want to do is set the header's restart interval to the next 16-bit integer. And then sticking with our pattern of checking if the length minus the number of bytes we've read is not equal to 0, then we have an invalid marker. In our print header function, let's print the restart interval. That's as simple as printing the restart interval just like this. And then as usual, in our marker reading loop, let's move the break to after reading the new marker. Now our cat.jpg file that we've been using doesn't have a restart interval marker, but let's test this on another JPEG file that does. Here's a picture called gorilla.jpg, and this JPEG uses restart intervals. So let's run our decoder on Gorilla. Run make again, and then this time run it on Gorilla. Now we see we're reading a quantization marker and a restart interval marker. Here are those quantization tables. The start of frame isn't initialized because we haven't read the start of frame marker for this file yet, so the dimensions are still their default values of 0. But now we see the restart interval is 57. So the Gorilla resets the relative value that is added to the DC coefficient every 57 MCUs. So now we are ready to talk about the problem I mentioned at the start of the video regarding some JPEG images that are inconsistent with the start of frame. We will run this on Gorilla again, but let's move the break so that it continues after the restart interval and gets to the start of frame, and then we'll break after reading the start of frame. Alright, so we will make, and we will run it, and it says error invalid component ID 0, and that was during the start of frame marker. In our function for reading the start of frame marker, we only accept component IDs between 1 and 3. We reject component IDs that are equal to 0 or greater than 3. That's simply because we know the rules are component IDs are either 1, 2, or 3. But this file, for some reason, uses component IDs 0, 1, and 2. That should be completely illegal. However, most JPEG decoders will correctly render the image anyway. This is something you'll notice a lot, that files can bend or break the rules in a lot of ways, and JPEG decoders and image viewers will decode them anyway and still do their best at showing you something, even if some rules were broken. For the most part, we aren't going to allow that. We are going to be pretty strict with the rules, but this will be one case where we will try to load the image anyway. The simplest way for us to handle that is to have a flag in our header called 0based and initialize that to false. If this flag is false, that means the color IDs are 1, 2, and 3. And if we discover a color component whose ID is 0, we will set the 0based flag to true. Back in our function for reading the start of frame marker, we have this loop for reading each color component's data. And here is where we will check for a component ID of 0. If we do see a component ID of 0, we will set the 0based flag to true and change the ID from 0 to 1. That way, the future iterations of this loop, we will also add 1, so that when we see component ID 1, we change it to 2, and when we see component ID 2, we change it to 3. That way, after this loop is finished, it doesn't really matter whether or not the color component IDs are 0based, because we forced them into the usual 1, 2, and 3. So the first step of that is if component ID is 0, then set the header's 0based flag to true. Regardless of whether or not we just set that flag to true, if it is set to true, we need to add 1 to the component ID. That way, this will happen for all 3 components. 0, 1, and 2 will be changed to 1, 2, and 3. This makes it so that our other comparisons don't need adjusting. Nor does our logic here, where we assume we will always subtract 1 when accessing our array of color components. And that should fix it, so let's try this on Gorilla again. And you see this time it did not print any errors. Before we got invalid component ID 0. Now it continued along and read the entire start of frame, so we can see the frame type, baseline C0, the dimensions, and we see the correct association between the component IDs and their quantization table IDs. Now it starts to get a little more complicated and a lot more interesting. The next marker is the marker for defining Huffman tables, or the DHT marker. This marker has the value FFC4. We mentioned before that the start of frame markers have the values C0 through CF, with the exceptions C4, C8, and CC. This is the first of those 3 exceptions. Then the length, of course. And now this is going to have some similarities to defining quantization tables in that we will repeat the next steps in order to account for the entire length because this marker might define more than one Huffman table. So let's talk about the format of one of these tables. We've already talked about codes and symbols, but for now let's not worry about the codes. The codes are what you actually encounter in the Huffman coded bitstream, but as we'll learn, we actually calculate or generate those codes. In this marker, what is defined, what we read, are the symbols. So ignoring codes for now, let's talk about what symbols are and how they're used. Huffman symbols are 8-bit values that contain two pieces of information, one in the upper nibble and one in the lower nibble. Remember that when we are using a symbol, it's because we are decoding a coefficient in an MCU, and that we are decoding the coefficients from the Huffman coded bitstream and traversing the MCU through the zigzag order. Now, the upper nibble of a symbol tells you how many zeros are preceding the current coefficient. That's because if there are coefficients whose value is 0, sandwiched in between two coefficients that are non-zero, we can use this trick to skip encoding the zeros entirely. Instead of encoding the sandwiched zeros on the next non-zero coefficient, we simply squeeze in a little bit of information about how many zeros were just skipped. The lower nibble is the length of the coefficient that you're trying to decode in bits. Now, because each of these is a 4-bit number, they can only possibly have the values 0 through 15, or 0 through f. For the number of zeros, all values are possible from 0 through 15. The current coefficient you're decoding might be preceded by 0 zeros, or it might be preceded by 15 zeros. So this can be anything from 0 to 15. Now, we haven't talked in much detail about the format of the coefficients at this point, since they are the quantized discrete cosine transform coefficients, but their length can only be between 1 and 10 bits long. So this value is going to be between 1 and 10. You shouldn't have coefficients of length 0, and you shouldn't have coefficients of length 11 or longer. Now, this here is 16 different possibilities, and this is 10 different possibilities. So 16 times 10 implies 160 possible symbols. There should be 160 symbols to allow for all combinations of number of zeros to skip and the length of the following coefficient. However, there are two special symbols. Consider this situation where after encoding the first coefficient, if we follow the zigzag order, we pass through exactly 15 zeros before we get to the first non-zero coefficient. In this case, we would have a symbol for the coefficient 50, and then immediately next we would have a symbol for the coefficient 5. Because we know the upper nibble of this symbol will contain the number of zeros that precede the 5, which is 15, this symbol will start with F, or 15. And then the lower nibble of the symbol is the length in bits of 5, which is 3. So we would need the symbol F3 for this situation. But then consider this. What if instead of the 5 right here, there was one more 0 and then the 5? Now we have 16 zeros preceding the 5, and we can't store that in the upper nibble of the symbol because 16 is a 5-bit number, not a 4-bit number. Instead, we have a special symbol, F0. This symbol means skip 16 zeros, despite the fact that f equals 15. So earlier with the symbol F3, we skipped 15 zeros, and the next coefficient was length 3. When this is 0, we skip 16, not 15. So in this situation, we would have the symbol for 50, whatever that is, followed by F0, which skips all 16 of these zeros, then followed by 0, 3, which means there are no more zeros to skip, and that the coefficient has a length of 3. Now you can probably predict what would happen if there was yet another 0. If the 5 was here, then the next symbol would be 1, 3. Skip 16 zeros, skip a 17th, and then read the coefficient. And of course, you can stack the F0 symbols as much as you need. So here we have 33 zeros before the 5. So we have one F0, which accounts for 16 of them, another F0 for another 16, and then the symbol 1, 3 for the 33rd 0. Now, the last special symbol is one we talked about in episode 1. After this 5 is encoded, every other coefficient is 0, so we don't have to encode these zeros at all. After the 5, we put a special symbol that tells the decoder to move on to the next MCU. This symbol is 0, 0. It doesn't mean to skip 0 zeros and that the next coefficient is of length 0, like our rules would suggest. It's just a special symbol that means stop. Every other coefficient is 0. So we have these 160 basic symbols plus F0 plus 0, 0. But we're still not done. Consider the DC coefficient. It will obviously never be preceded by any zeros. In other words, the upper nibble of the symbol should always be 0. Because of this, the DC coefficients get their own Huffman tables, separate from the Huffman tables used for the AC coefficients. So for DC Huffman tables, the upper nibble will always be 0, because the coefficient cannot be preceded by zeros. So we only have one option for the upper nibble. The length of the DC coefficient can actually be between 0 and 11. So the AC Huffman tables can have these 162 symbols, while the DC Huffman tables are limited to these 12 symbols. Now let's return to the format of the marker for Huffman tables. Similarly to quantization tables, we first start by reading one byte, which is the table info. And again, this is broken up into two pieces of information. The upper nibble is either a 0 or a 1. Again, basically a Boolean value, where a 1 means this is an AC Huffman table. And then, of course, a 0 means it's a DC Huffman table. The lower nibble is between 0 and 3, and that is the table ID. Now, the table IDs are not shared between the AC and the DC tables. So you will have a DC table with ID 0, and you will also have an AC table with ID 0. Now, I briefly mentioned in episode 1 that the codes that will be in the Huffman coded bitstream will have variable lengths. Not all the codes will be the same size, even though we know the symbols are all 8 bits. So all of these 8-bit symbols correspond to codes of different lengths. And the codes can actually range in length from 1 to 16 bits long. We need to know the length of the code that each symbol corresponds to. So we read 16 bytes, where each byte tells us how many codes there are of that length. So the first byte we read of these 16 is how many codes are 1 bit long. The 10th byte we read will be how many codes are 10 bits long, and so on. Then we read another chunk of bytes, which are the symbols themselves. Now the number of bytes we read is equal to the sum of these 16 numbers. And usually that will be 162 for an AC Huffman table or 12 for a DC Huffman table. However, it can be less because the encoder that created the JPEG file could have optimized the Huffman tables and eliminated symbols that happened to never be used. So we can't make any assumptions about how many symbols there will be. Now, as I said, this marker could define many Huffman tables, so we need to repeat these 3 steps until we've accounted for the entire length. Before we leave our drawing slides, let's think ahead about the struct we're going to have to make for Huffman tables. Basically, we're going to want to have 16 lists where each list contains all the symbols that correspond to codes of the same length. So that the first list holds all the symbols with codes that are 1 bit long. The 16th list holds all the symbols with codes that are 16 bits long. And some of these lists might be totally empty, which is fine. But this basically leads to a data structure that is actually more complicated than we need. This would be something that is kind of like a jagged array. So basically what we're talking about is an array that is 16 long, and each of these elements is actually also an array, and they all have variable lengths. So what it means for a 2D array to be a jagged array is that the rows have different widths. The code lengths could actually have a distribution like this. In fact, this really is the distribution of code lengths for the standard AC Huffman table for luminance. So hopefully this visualization makes a little bit more clear what I mean by a jagged array. A jagged array is basically like a 2D array because you can go down in the y direction, which is like choosing the first index into the 2D array. Then you can pick an x-coordinate to select an element from inside that row. However, with a normal 2D array, the width of a row is always the same, and that is not the case in a jagged array. In some languages, representing jagged arrays is easy. In C++, it is not. We would have to do some annoying pointer management and memory allocation. It's overall a mess and not worth it. The quickest workaround you might think of is to make these rows the maximum possible width, which is 162. But then we're going to be just wasting almost all the space, and that's not really worth it either. So instead, let's do this. Instead, let's make a one-dimensional array whose size is 162, and in that array we will store all the symbols, a maximum of 162 of them, and we'll store them in the same order that we read them from the file. However, we'll still need a way to know how the symbols are supposed to be grouped. So if these two symbols with codes of length 2 are placed at the start of our 1D array, and this symbol with the code of length 3 is placed right after, it will be at position 2 in this one-dimensional array, and these 3 symbols will be placed immediately next to this symbol. We somehow need to know where each new section begins in this array. The best way to think of it is like this. Symbols of codes with length 2 begin at index 0 and stop once you hit index 2. Symbols with code of length 3 begin at index 2 and stop when you've gotten to index 3. And symbols of codes with length 4 start at index 3 and stop at index 6. But if we recognize that the green section begins at the same index that the red section ends, then we don't need 2 pieces of information here. We only really care that the green section begins at index 2, and likewise for the blue section. We don't exactly care where the green section ends, only where the blue section begins. Also think about the symbols for codes of length 1. There are none of them. That's kind of like saying they start at index 0 and also end at index 0. And then the usual, we don't care where they end. So all we care about is the starting positions of every section. So what if we had an array that was 16 long? Then in this array, at each position, we stored the starting index into the symbols array for symbols corresponding to codes with this length. Then the starting index of codes of length 1 is 0. The starting index of symbols with codes of length 2 is also 0. The starting index of symbols with codes of length 3 is index 2. The starting index of the blue section is index 3. This might seem pretty strange, but there are actually a lot of benefits to this. We can infer quite a bit of information. Consider this. After we put all of these symbols into our one-dimensional array, we know the red section begins at index 0 and goes up to, but not including, index 2. Starts at 0 and goes up to, but not including, index 2. This also shows us that the number of red symbols is 2 minus 0, which is 2. And in fact, we can see that that is true. We know the green section begins at index 2 and goes up to, but not including, index 3. And the number of green symbols is 3 minus 2, or 1 green symbol. Of course, this blue arrow is pointing to the start of the next section, which is index 6. The blue section begins at index 3, goes up to, but not including, index 6, and the number of blue symbols is 6 minus 3, or 3 symbols. So when trying to consider, for instance, all of the red symbols, we care about these two values in this array. And we use these as starting and ending indices into the symbols array, where the end index is non-inclusive. And that setup will be true no matter which length we are interested in, except for the very last one. In this example, the symbols for codes of length 16 begins at index 37. So this offsets array would have a 37 in the last position, and usually we would look into the next position in the array to find the ending index for this group of symbols. It might seem not necessary because it would just be all of them or the rest of this array, but that's only going to be true if this Huffman table uses all 162 symbols, which, as I mentioned before, it might not include all of them if the Huffman table has been optimized to exclude unneeded symbols. Or if this is a DC Huffman table, in which case there will only be 12 symbols anyway. So our offsets array will actually be 17 long, so that we have a starting and ending index for all 16 groups. And the value here at the end will usually be 162. At least for AC Huffman tables. So this use of a one-dimensional array of size 162 for the symbols and this array of size 17 for the offsets allows us to store all possible Huffman tables and never deal with anything like an ugly jagged array. Now that was quite a lot of information, but now we are ready to read this kind of marker in our decoder. So we've already talked at length what this Huffman table struct is going to look like. We need our list of offsets, which is a list 17 long, and we want to initialize that with all zeros. And we need our symbols array, which is 162 long, and also initialize it to 0. And for the same reason that we need the set flag in the quantization table, we want the set flag in the Huffman table struct as well. Then we need to add some Huffman tables to our header, but we need to store the DC Huffman tables and the AC Huffman tables separately. And because the ID can be between 0 and 3 for each kind of Huffman table, our array needs to have a size of 4 and have an array of AC tables in the same way. And that's all we need to add here. In our marker reading loop, check if current equals define Huffman table. Add the read Huffman table function. Just like with reading quantization tables, we're going to want length to be a signed integer in this case, so that we can detect if length goes below 0. And after reading the length bytes, we can subtract 2 right away. And then loop while length is greater than 0. The first thing we have to do is read the table info byte. From that, we extract the table ID, which is the lower nibble of the table info byte. And we determine whether this is an AC table or a DC Huffman table based on the upper nibble of the table info byte. So we get the upper nibble by shifting to the right 4 bits, but we can store this directly as a Boolean, which will set this to false if the upper nibble is 0 and set it to true otherwise. Like usual, we want to check if the table ID is valid. It is invalid if it's greater than 3. Now let's get a pointer to our Huffman table by accessing into the 2 lists from the header, but which Huffman table list from the header we use depends on if this is an AC Huffman table or a DC Huffman table. So if this is an AC table, the Huffman table we are reading is from the AC tables list, and we use the index table ID. Otherwise, the same thing, but we use the DC table list. Once we have our table, we can set its set flag to true. Next, we need to read the 16 bytes, which represent how many symbols correspond to codes of each length. We're going to want to keep a running total of how many total symbols there are. And we also want to initialize the first element of the offsets array to 0, which is probably a little redundant, but it helps us be extra certain that this value is set correctly. Then we need the running total of all the symbols and initialize that to 0. Then we need to read the 16 bytes. This loop will start I at 1 and go up to and including 16 because those are the positions into the offsets array that we need to set to their correct value. First, though, we will keep track of how many symbols we have total by reading the next byte and use the current value of all symbols to set the next value in the offsets array. We know the maximum number of symbols is 162, so if all symbols is greater than that, we have another error. And now, because we have set up our offsets array, which is the hard part, we just have to read the next chunk of bytes, which are all the symbols, and store them in a straight line in our symbols array. Now, the number of bytes we just read is 1 for the table info, 16 for the symbol counts, and all symbols worth for these symbols. We need to subtract that total from length so that our loop will terminate correctly. And then we want to check for the situation where our while loop has finished, but length is not exactly equal to 0. And that is the whole function for reading Huffman tables. Let's modify our print header function to print the Huffman tables that we read. In print header, we'll add that right after printing the start of frame info. First, we print the DC tables. For all 4 of them, for every table that is set, we print the symbols like this. For all 16 code lengths, we print the code length. And then for every symbol, starting at this code length up to but not including the beginning of the next code length, we print that symbol. And then before moving on to the next code length, we print a new line to separate essentially the rows of our jagged array. And then we do the exact same thing for the AC tables. Actually, I should add standard hex here before printing each symbol so that we can really clearly see the upper and the lower nibble for each symbol. And lastly, let's move this break to after reading the Huffman tables. And now let's try running this on cat again. Now we have a whole lot more output. Let's take a look. It starts out the same. We read all of our markers, but now we're also reading the defined Huffman table marker. Print the quantization tables like before. Print the start of frame information like before. Now we print the DC tables. Table ID 0 has the symbol 0, which corresponds to a code of length 2, even though we don't know what that code is yet. Symbols 01 through 05 correspond to codes that are 3 bits long, and you can see the rest here. The other DC table, ID 1, has the same symbols, but a slightly different distribution. And these are the easy tables, because they only have 12 symbols. AC table ID 0 has all 162 symbols, and you can see the distribution here. If you really look through it, you can see the special symbol 00, and the other special symbol F0, and all of the other 160 symbols are the basic symbols. For this JPEG file, table ID 0 is used on the luminance channel, and table ID 1 is used on the two chrominance channels. And there we go. That's a pretty complicated marker, but we're finally done. We only have one big important marker left. The last important marker we need to talk about is called the start of scan. A scan refers to a Huffman-coded bitstream, and it means a bitstream that contains information for every MCU from left to right, top to bottom in the image. For baseline JPEGs, there will only be one scan, and that one scan contains every coefficient of every MCU. But this marker still contains some other data before the actual scan begins. First, the marker for the start of scan is FFDA, then the length bytes. Then we read a byte that tells us the number of color components in this scan. For baseline JPEGs, this value should be the same as the total number of color components in the image, but the reason this is included here is because for progressive JPEGs, a scan might include information for only one color channel instead of all of them. Next, we will loop and read a couple pieces of information about each of the color channels in this scan. The first thing we read is the component ID, and then we read the Huffman table IDs used on this color channel. Like we've seen many times now, this is broken up into the upper nibble and the lower nibble, where the upper nibble is the DC Huffman table ID and the lower nibble is the AC Huffman table ID used on this color component. Then we repeat these two steps based on the number of color components in this scan. Then we read 3 more bytes that only have to do with options regarding progressive JPEGs, meaning these 3 bytes should have the same 3 values for all baseline JPEGs. The first 2 of these bytes are the start of selection and the end of selection, and these indicate in the Huffman-coded bitstream for each MCU what are the starting and ending indices of the coefficients that are present in the scan. Again, because baseline JPEGs include all the information in the scan, the start and end indices should be 0 and 63. So we should always see 0 and 63 when decoding baseline JPEGs. The last byte is called successive approximation. Again, it is only for progressive JPEGs. This means that in a progressive scan, the coefficients that you read out of the Huffman-coded bitstream might only contain some subset of bits in each coefficient. For baseline JPEGs, we know that we will be reading the entire coefficient, all 8 bits of each coefficient, and the value for the successive approximation must be 0. This isn't super important right now, but the successive approximation is also split up into the upper nibble and the lower nibble. So that will be important later, but for now, we just know both nibbles must be 0. So when reading the start of scan, after we loop to read information about each color channel, we read 3 more bytes that must be 0, 63, 0. This length value only counts up to the end of these 3 bytes. So after you read this byte, you will have already accounted for the entire length. But this is where things get a little bit weird. After the last byte of the start of scan marker, the actual start of scan begins. So after this point, begins the Huffman-coded bitstream. Things start to look a little bit strange in the bitstream, so let's talk about exactly what this is going to look like. For the most part, this is just going to be an enormous stream of bytes that hold all the codes and the coefficients. And as we've talked about, the bits in this data don't have to respect byte alignment. So if this is some byte in the bit stream, and this is the next byte following that, and there is a piece of data 5 bits long, and it happens to begin at this bit inside this byte, then it will start at the 2 least significant bits of this byte, and whatever bits are left get placed in the next byte starting at the most significant bit of that byte. So if we number the least significant bit, bit 0, and the most significant bit, bit 7, this stored value is placed at bit 1, bit 0, bit 7, bit 6, and bit 5, of 2 different consecutive bytes. At this time, though, we're not going to really be analyzing the bit stream, just reading it out of the file and storing it in a data structure. That way we can close the file and then move on with processing the MCUs as a separate step after the file has been fully read and closed. So when we're reading this data, we will just take each byte and store it somewhere, read the next byte, and store it also. But there are a few things we need to watch out for. Markers are allowed to show up in the middle of a Huffman-coded bitstream. And we know markers begin with FF. So every time we read a byte and we're about to store it, we need to check first if it is equal to FF. And if so, escape from our normal process of just reading bytes and storing them. Now, in baseline JPEGs, there aren't actually that many markers that can show up in the bitstream. Before, when we were talking about the restart intervals, we were talking about the DRI marker, the defined restart interval marker. And that marker shows up towards the beginning of the file and tells you what the restart interval is. In addition to that marker, there are 8 more called RST0 through RST7, and they have the values D0 through D7. These markers show up in the Huffman-coded bit stream after the correct number of MCUs have passed. So if this bit here was the last bit relating to the end of an MCU, such that that MCU was also the end of the restart interval, then the remaining bits in this byte would just be 0. And then the next 2 bytes would be FFD0. If the restart interval was 4 MCUs, and this was the end of the 4th MCU, then it will be followed by the restart 0 marker. Then after 4 more MCUs worth of data, that byte will be followed by the restart 1 marker, and so on. After a restart 7, the next time you need a restart marker, it will be restart 0. The use of restart markers is kind of rare. It's not used in most JPEGs, but you still definitely see it often enough. It's also really not that useful. I think the idea is that if there is any kind of data corruption in the bitstream, as soon as you get off by a little bit, you have no hope of constructing a useful image from that point forward. So the restart markers allow you to just resynchronize your decoding every so often, so that even if there is some amount of data corruption, it will only cause some artifacts in the general area of the image where the corruption happened, and then soon after, your decoder would become synchronized again, and you would have no more artifacts in the image. But I don't think it turns out to be that helpful. It's more so just annoying that we have to handle the restart markers. But it isn't that big of a deal. We don't even really care about which restart marker it is, whether it's restart 0 or restart 1 or restart 2, doesn't matter. We'll just identify it as restart marker, skip it, and then move on. It's also worth mentioning that the standard says that any number of FFs in a row are allowed before the actual marker value. So if the bitstream contains FF, FF, D0, this is perfectly allowed. We just skip 1 or more FFs and read the marker. And this is actually true all the time, not just during the bitstream. This is true from the beginning of the file also. The only other kind of marker that we should ever encounter in the bitstream is the end of image marker, which is equal to D9. The only other thing we have to worry about is that with this system, we've made it impossible to encode a literal FF in the bitstream. Based on the Huffman codes and the coefficients that are in the bitstream, what if this byte just happens to equal FF? Even though these bits represent codes and coefficients, it's definitely possible that all of the bits happen to be set to 1. But given everything else that we've talked about, we will detect that it's equal to FF and then try to read the next byte as a marker, hoping that it's a restart marker, another FF, or the end of image marker. So if the bitstream contains a literal FF, we will know to store this in our bitstream data structure if it is followed by 00. If an FF is followed by 00, ignore the 00 and pretend it doesn't exist, and then store the FF in our bitstream data structure. Otherwise, if we see an FF and it's followed by another FF, just ignore one of them and look at the next byte again. Or if the FF is followed by one of the restart markers or the end of image marker, then handle those accordingly and do not store the FF or the marker in our bitstream data structure. Otherwise, FF is followed by some other value, in which case we should report that as an error. Okay, so now let's try to code all of these rules into our decoder. First, let's modify some of our structs to account for the start of scan data. We learned that the start of scan tells us the Huffman table IDs that get associated with each color component, so let's add that here to our color component struct. We also learned about the start of selection and end of selection, which, by the way, are also called spectral selection. And we learned about successive approximation, and that was broken up into the upper nibble and the lower nibble. So let's add that to our header. Lastly is the Huffman-coded bitstream, which I'm going to put into the header struct here, but that's a little bit inappropriate because at this point, our header struct is essentially the entire JPEG file. But I don't really want to overthink our naming here, so we'll leave it the way it is. Also, I've been trying to avoid anything too fancy, but I'm going to go ahead and use a standard vector for the bitstream because it's going to be the least painful way to store the bitstream, given that we don't know its size before we begin reading it. So we need to include vector. and we want to add a vector for the Huffman data to our header struct. And that'll do it. So let's read the start of scan in our marker reading loop. We'll add that right here. Then we'll add the read start of scan function. We'll add that right here. Now recall that earlier, the start of frame marker set the number of color components in our header struct. Initially, the number of components defaults to 0, and the start of frame will set it to a non-zero number. So here in the start of scan, we can detect an error if the header's number of color components is still 0, because we should never run into the start of scan marker before reading the start of frame marker. Then we read the length like usual. Now also recall that reading the start of frame, we set all of the used flags on our color components to true to keep track of which color components we successfully read the quantization table ID for. We want to use that used flag in the same way here when reading the Huffman table IDs, but before we do that we have to set all of the used flags back to false. We do that just like that. The next byte we read is the number of components used in this scan. And then we want to loop based on the number of components. In this loop, the first byte we read is the color component ID of this color component. Again, of course, this component ID will hopefully be 1, 2, or 3, but in the case that our start of frame earlier indicated that the color component IDs in this file are 0-based, we need to add 1 to the color component ID. We also have an error if this component ID is greater than the number of components in this image. At this point, we've guaranteed we have a valid component ID, so we can get a pointer to the color component from our header. If this color component's used flag is already set to true, that means we have ran into this color component twice in this same loop, which is a problem. Otherwise, we can set its used flag to true. Then the second byte we read for this color component is the Huffman table IDs. And the upper nibble is the DC table ID, and the lower nibble is the AC table ID. If either of these IDs are greater than 3, that's an error. That's all that needs to be done for each color component, so this is the end of our for loop. The only thing left to read for the start of scan is the spectral selection and the successive approximation bytes. And then the successive approximation byte gets stored as its upper nibble and its lower nibble. Then we need to verify that these values are 0, 63, 0, and 0. That looks like this. If start of selection is not 0, or end of selection is not 63, we have an error. And if successive approximation high is not 0, or successive approximation low is not 0, we also have an error. The last thing to do is to verify that the length value we read at the start of this marker matched up with the number of bytes we read based on the number of components. And there we go, that reads the start of scan marker, but we still have to read the Huffman coded bitstream. Next, we need to adjust our marker reading loop to read the Huffman coded bitstream after reading the start of scan. First, let's move the break. Instead of breaking after reading the Huffman table marker, break after reading the start of scan, and this time we will keep this break here for good. We'll have a second while loop back to back with this while loop, and the second one will be responsible for reading the Huffman coded bitstream. Also, in this while loop, there are a couple more markers we can look for that we haven't talked about yet. So real quick, let's go through all the markers and mention the ones that we haven't talked about yet. Here we have the 13 start of frame markers that we've already talked about, and we will only be handling baseline C0. Next is the define Huffman table marker. This next one is an unused marker. It's just called the JPEG extension marker. It doesn't have a use, and we should never encounter it. The next one is the marker for arithmetic coding, which is an alternative to Huffman coding. We are not going to be covering that at this time. Then the restart markers we've talked about. We have the start of image, the end of image, start of scan, and define quantization tables, all of which we've talked about. We have not talked about defining the number of lines, the hierarchical progression, or the expand reference components, but all of those are non-essential. They're extremely rare, and I've never seen a JPEG file that uses them, but even if they are used, they can be skipped. And then there is the define restart interval marker we talked about. The APPN markers. These here from JPEG 0 through JPEG 13 are reserved for future versions of the JPEG standard that include more new options that need new markers, but so far they're still unused and we shouldn't ever encounter them in a JPEG file either. Then there's the comment marker, which is simply the marker FFFE followed by the length, followed by whatever the encoder chose to put in the comment. Those are always skippable. And then last is the TEM marker, which I don't really know what that's for, but it shouldn't have a length. So after reading FF01, you immediately read the next marker. Okay, now that we've talked about the miscellaneous markers, let's add a few more quick handlers for most of those in our first while loop. Let's add a really short function for reading a comment. It's basically going to be identical to reading an APPN marker. So that just looks like that. Then we can add the handlers for the rest of the markers. The rest of these markers kind of fall into one of two categories. Either they're non-essential and we simply skip them, or it's an error for us to encounter that kind of marker at this time. So for category number 1, I'll just paste that in. So after our last serious marker, we can read comments, skip any one of the other markers that has a size by calling our read comment function also. That is all the unused markers, define number of lines, define hierarchical progression, and the expand reference components, as well as the TEM marker, which has no size, so we don't do anything. And like I mentioned, there can be any number of FFs in a row before seeing a real marker. So here, if last equals FF and current equals FF, simply overwrite current with the next byte. That way last still equals FF and current equals the next byte, and then continue so that we don't overwrite both last and current. Then we have the markers that should not be encountered at this time. That is the start of image marker. We shouldn't encounter a start of image marker after beginning the file. This is allowed in some way, but that opens up a can of worms that I don't want to deal with, and it's such a rarely used feature anyway. Likewise, end of image is not allowed because we must encounter the start of scan before the end of the image. Arithmetic coding is not supported because we are only using Huffman coding. Any of the other start of frame markers other than the one we already handled is not supported. The restart markers should not be seen outside of the start of scan. And then finally, the catch-all else, we have some mysterious marker. Whoops, missing an infile.close there. So if we are outside of our first marker reading loop, one of two things happened. Either we hit the break statement after reading the start of scan marker, or one of the many functions that reads a marker set the valid flag to false on the header struct. So now we need the loop to read the Huffman coded bitstream, but let's only bother entering that loop if the header is still valid. Now in this loop, we're still going to use last and current, similarly to how we did in the first loop, but we're only going to read 1 byte at a time because of the way we have to check for markers and store bytes into the Huffman coded bitstream. It's easier to read 1 byte at a time. First, we'll prep current before beginning the loop. Now we'll start the loop of reading the scan. This loop will only terminate when we successfully read the end of image marker or when we encounter some kind of error. We will always break manually from this loop, so we can make it an infinite loop while true. Like our first while loop, we will check if the file ends prematurely. Otherwise, we can read the next byte, but since we're only reading 1 byte at a time, what we're going to do is scoot the value of current into last, and then read another byte and store it into current. This way we can look at 2 bytes at a time to see if we're looking at a marker, and on the other hand, if we're not looking at a marker, we store last into the Huffman coded bitstream. So that right there is our 2 possibilities. Either we're looking at a marker or we're not. If last is equal to FF, we might be looking at a marker, but we might not because maybe FF is supposed to be a literal value in the bitstream. To figure that out, we have to look at the value of current. If current is equal to end of image, we can break. We are finished reading the start scan. Or current could be equal to 0, 0, which means ignore the 0, 0 and put the FF into the bitstream. To do this, we will add last to the header's Huffman data vector. And to ignore the 0, 0, overwrite current with the next byte. Or current could be a restart marker. Like we mentioned, we don't exactly care which restart marker this is. We'll just overwrite this marker value with the next byte. In this case, if last equaled FF and current equaled RST0, we'll overwrite RST0 with the next byte, come back around to the beginning of this loop, we will move that new byte into last, and overwrite current with yet another byte. That way, by doing this, we ignore both the FF and the restart marker itself. And the next time around on this loop, begin considering 2 new bytes. Or it's possible we're looking at multiple FFs in a row. In this case, do absolutely nothing, because at the top of this loop, current, which is FF, will get moved into last, which is already FF, then current will be overwritten with the next byte, and if this is a marker, then last and current will equal FF and a marker, which is what we want. Otherwise, last is equal to FF, but current is equal to some invalid marker. So we'll print that out just like that. Now all of this is the situation where last is equal to FF. If last is not equal to FF, we simply want to add last to the Huffman data. And that's it. That's how you read the Huffman coded bitstream from the start of scan. Once we reach this point, either we skipped the entire second while loop because the header was already not valid, or we have entered and exited the second while loop. Right before returning the header, we can do just a few more error checks. All we're going to do is verify that the number of color components is either 1 or 3. If it's not 1 and it also isn't 3, we have an error. The other thing we can do is, for every color component, we can look at that color component's quantization table ID, DC table ID, and AC table ID, and make sure that the table with that ID is set. If any of those tables are not set, then that means the start of frame or the start of scan told us that a color component uses a table that was never defined in a DQT or DHT marker. And there we go. The very last thing we have to do is close the file for good. Now we can make our final adjustments to our print header function. So let's add a section for the start of scan right after printing the Huffman tables. Here we can print the start of selection, end of selection, successive approximation high, and successive approximation low. And for every color component, print the ID. And for each color component, print the DC and the AC Huffman table IDs. Lastly, let's print the size of the Huffman data. We don't actually print all the data out. That would be ridiculous because it's usually thousands and thousands of bytes. But let's print its size so we can verify that we got something. And there we go. That is everything. So let's run this on cat one more time. And it looks mostly the same as before, except after printing all of the Huffman tables, we are now printing the start of scan information. The start of selection is 0. The end of selection is 63. The successive approximation values are both 0. And for the color components, component ID 1 is using Huffman tables 0 and 0, and components 2 and 3 are using Huffman tables 1 and 1. Last, we can see the size of the Huffman data is almost 30,000 bytes. And there we go. Now we can put the entire JPEG file into our structs. All the data is now in our hands, and now we can start doing some pretty cool stuff with it. I know this was another long episode, so thanks for sticking through it. I hope you found it interesting, and I will see you again next time in episode 3.